Low Earth orbit is currently reaching a point of saturation. Over the last decade, launch frequency has surged, building dense, interconnected commercial megaconstellations that now wrap the entire planet in a digital grid. Many of these projects, like SpaceX's Starlink, are now visible to the naked eye. They form long, uniform trains of light meant to provide global internet coverage, but their presence highlights a growing physical challenge. Operating this close to Earth means fighting a relentless headwind. Even hundreds of miles up, thin wisps of atmosphere create a constant drag. As satellites collide with these molecules, friction acts as a brake, steadily draining their orbital energy. To maintain their position, satellites carry specialized hardware for active station keeping. These dual circular thrusters use onboard propellant, usually argon, to provide the periodic bursts of momentum needed to stay aloft. This creates a hard limit on the mission's lifespan. Without that fuel, atmospheric drag is a guaranteed winner, eventually dragging multi-million-dollar assets into the furnace of the lower atmosphere. The cost of carrying this fuel is significant. On average, up to 20% of a satellite's total mass is dedicated purely to the station-keeping fuel and the heavy pressurized systems required to manage it. Launching that dead weight requires massive amounts of chemical energy. Companies essentially spend millions of dollars per flight just to lift the fuel they will later use to stay in space. And because these machines cannot be refueled, their operational life is set the moment they leave the ground. Once the onboard gas gauge hits empty, the satellite is discarded, left to burn up in the atmosphere. This is the Keplerian limit of classical astrodynamics. Under our current understanding of physics, we are forced to treat satellites as temporary, fuel-dependent rentals rather than permanent infrastructure. A potential solution lies in Dr. Jinhyuk Chung's dimensional interface model. It suggests that instead of fighting gravity with fuel, we can use the metabolism of space itself to provide thrust. While classical physics treats space as a passive vacuum, the 5D ICF framework views it as an active, elastic membrane. This interface has a finite capacity for stress and behaves with measurable rigidity. As a satellite moves through a planet's gravity well, it creates intense, localized metric shear. The model identifies this buildup of spatial tension as interaction mass, a dynamic energy reservoir that appears whenever the fabric of space is warped. To maintain its own structural coherence, the universe must stabilize this tension. It does this by venting the excess stress as a continuous stream of expansionary exhaust, pushing back against the source of the friction. This means space functions as a thermodynamic engine. It provides a built-in exhaust valve that generates physical thrust out of pure gravitational stress. Applying this to a real-world 800 kilograms Starlink V2 Mini requires a shift in how we plan orbital paths. The first step is lowering the satellite to a precise metric coordinate. At exactly 514.8 kilometers, the satellite enters a specific gradient where the Earth's gravitational stress is perfectly tuned for this interaction. When the satellite's inclination aligns with Earth's kinetic topological wake, it triggers a series of high-frequency microphase slips. This synchronization allows the satellite to harvest that expansionary exhaust as a constant source of momentum. Look at the balance of power. At this specific altitude, the blue bar, the power supplied by the universe's exhaust, perfectly negates the red bar of atmospheric drag. This creates a self-stabilizing governor. If the satellite dips too low, the metric gradient increases, triggering a higher exhaust surge that pushes it back up. This internal feedback loop means the framework can fully automate station keeping, removing the need for active propellant. Operating in a resonant coherence orbit changes the fundamental design of space hardware. Because the orbit is self-maintaining, engineers can strip away the fuel tanks and pressurization systems entirely. That 20% mass budget is instantly freed up. It can be reallocated to revenue-generating technology, like additional communication transponders, allowing a single launch to carry significantly more payload. This also alters the financial model of space. Without a fuel gauge limiting its life, a satellite's operational span is theoretically infinite, limited only by the durability of its internal electronics. Deorbiting also becomes a passive safety feature. By rotating the satellite's attitude out of alignment with the wake, operators break resonance. Drag immediately takes over, ensuring a rapid atmospheric burnup. This framework transforms satellite constellations from temporary, depreciating assets into permanent, self-sustaining infrastructure. The constants that make this zero-fuel orbit possible are not engineering shortcuts. They are fixed laws that appear to govern the universe at every scale. On a cosmological scale, this same venting mechanism provides a physical explanation for dark energy. The same expansionary exhaust we use to push a satellite is what drives the accelerated expansion of the entire universe. Those same mathematical values also precisely predict the energy transitions we observe in subatomic particles, showing a consistent behavior from the quantum to the cosmic. The same mechanics that save the aerospace industry billions in propellant costs also provide a functional bridge to the grand unified mechanics of the cosmos. We are no longer just fighting gravity. We are utilizing the metabolism of spacetime itself.